So we're going to officially define the trig functions of sine, cosine, and tangent. They are, in their simplest way of looking at them, they are just ratios. Just the same way 1 to 2 is a ratio, which you could also write as 0.5. In fact, sometimes the sine and cosine and tangent come out to be 0.5. So even though it may not be written with two numbers, it is still a ratio. Now, in the exercise that you did prior to this, and hopefully you did that, because they mean something, what you should have noticed is this, is that for the blue triangle, for example, for this triangle here, this little guy, when you compare this side to its hypotenuse, so for example, BC over AC, you get a certain number. And then since they are similar triangles, if you do the same thing with this red triangle here, and look at the corresponding side here, DE over, let's see, its hypotenuse, AE, you'll realize that they're the same. If you measured them and they were a little bit off, that's obviously understandable, that's part of science, but they are the same. And then of course you could carry this further. This compared to this, or I should reverse it, this over this, would also give you the same number, and so forth and so on. Which means that the size of the triangle doesn't really make a difference. All that matters is how big is this angle. If you want to change this ratio that we're talking about, this side to this side, then making it a bigger angle would change that ratio. But anything else, just making the whole triangle bigger or smaller, right, is not going to make a difference. And that's important. That means there is a special ratio for whatever angle this is, 22 degrees or whatever you measure it to be. I don't know what it was. But whatever that angle is, there is a special number that goes with it. If it's in a right triangle, this side over this side will always be the same number, no matter how big or small the triangle is. This side to this side will be the same. Put one over the other. This side compared to this is going to be the same. And that, my friends, is the sine of that angle. What do I mean by that? Well, let's get rid of all this ink for a second. We'll talk. So here's how we define the sine of an angle. I'm going to put tangent back up there. So first of all, in a right triangle, let's make sure we realize there are actually two angles involved that aren't the right angle. All right? We'll give this one 2 arcs and this one 1. That there are two angles. These definitions I'm about to give you depend on where you are standing, so to speak. If you are considering this angle, which we've been talking about, and I want you to imagine you're in a strange triangular room, and you're looking down on top of your head. This is the top of your head right here. If you were put into this corner because you were somehow, behaving inappropriately, then what side would you describe as the opposite? Well, from where you're standing, that would be the opposite side. And of course, another side that we can always identify in a right triangle, and doesn't even matter where you're standing, is the hypotenuse. In fact, in many cases, I would encourage you to identify that first. So you have a right triangle. Based on where you're standing, hypotenuse will be the same no matter where you're standing. It's always the longest side. But based on where you're standing, you will have an opposite side, and you will have, and this is always the third one I identify because it's the trickiest, an adjacent side. I think that's right. I'm not a great speller. You'll discover that as things go on. So we have hypotenuse, opposite, and adjacent. Notice, switch colors. If my angle was this one, I'll use another Greek letter phi. By the way, this letter here that you see here, O or 0 with a horizontal line through it, that's theta. That's the first choice for variables that are angles. Second choice, kind of like x is for other numbers. The first choice, the second choice would be phi, a circle with a vertical line through it. For that angle, if you were standing there, would this be the opposite? And the answer is no, right? The opposite would be here. So the roles of opposite and adjacent can switch depending on what angle you're relative, what angle you're looking at them relative to the, that makes no sense, you know what I mean? Depending on where you're standing, that's the way I like to look at it. But from whatever angle you're taking as your reference point, there you go. So, this, for the red angle, this would be the opposite. This is still the hypotenuse, and this over here would be the adjacent. Now we're oftentimes going to deal with this angle down here, which I shouldn't make in red because, right, you'll get confused. So, the ratio that we were talking about a minute ago was this side compared to this one. Or in the other larger triangle, for example, it was this side over this one. So how would we describe that? If you're standing here at theta, what would that be? That would be the opposite side over the hypotenuse. So opposite side over the hypotenuse. That gets a special name. That is the sine of the angle. So the sine of an angle is opposite over hypotenuse. All right. Let's look at some other possibilities. Well, we have hypotenuse and opposites and all that. So let's see what we got here. So we have, for this triangle here, all right, we got opposite here. For assuming we're dealing with this angle, this is hypotenuse, and this is the adjacent. So what's cosine defined as? We need a different pair. It is going to be defined as the adjacent over the hypotenuse, that ratio. So when we consider the adjacent side divided by the hypotenuse, that is what's called the cosine of the angle. So we've got a combination of opposite and hypotenuse and adjacent and hypotenuse. What's the only combination left? Something involving the opposite and adjacent, or adjacent and opposite. Well, what we look at is the ratio of the opposite over the adjacent. And that is the tangent. So the tangent of an angle, this angle, would be, it's going to be the opposite over the adjacent. So there are just a set of ratios. Every possible angle has these three values. You'll note that, for example, sine and cosine, if you think about it a little bit, the longest side is always the hypotenuse. So the sine and cosine, this ratio, for example, can never be more than 1. And even 1 is kind of a strange case, but it's never going to be more than 1 because this has always got to be bigger than this, or at least equal to it in some strange cases. Tangent has a much wider range of values. In this case, for the triangle I've drawn, the tangent of this angle would be less than 1. But if you think about it, what about the tangent of this angle? Sorry, wrong. What about this angle? Well, its opposite is much longer than its adjacent. So in this case, the tangent of this angle here would be more than 1. So tangent has a bigger range of values. The way that folks are going to have you remember this is as follows. They're going to have you remember as Sohcahtoa. Now, this wasn't invented. I guess invented is the right word when I was a lad, but if it helps you, go ahead and use it. For me, you just memorize the 3 things I just said. Just memorize them. That's all. You'll use them enough. Memorize them. They're going to help. You're going to help throughout all math and science. But Sohcahtoa, let's see, S-O-H-C-A-H, you might be able to see where I'm going with this, T-O-A, Sohcahtoa. If it helps you remember, use it, because all it stands for is the sine is the opposite over hypotenuse, the cosine is the adjacent over the hypotenuse, and tangent is opposite over adjacent. If it helps you remember it, have at it. But like I said, sometimes in life it's just as simple as just that, and that. know them. If someone says the cosine, be able to picture what they're talking about. Now, try the homework problems. They're going to look something like this. I'm going to give you, say, for example, here's a right triangle. We're going to call that phi, and this theta, and I'm going to make up some numbers here. So I'm not guaranteeing, like if you were to measure these, I'm not saying these numbers would be correct, but I'm just going to make them up. So let's say this is, we can do letters, we can do numbers. We'll do numbers first. Let's say this is 18, this is 11, and this is 23. There we go. So I don't have to simplify. Now, what would be try a little quick test. What would be the sine of theta? And think about it. Maybe pause the video. You know, from dealing with theta, what's its opposite? That would be 11. And I know that sine is opposite over hypotenuse, and the hypotenuse is 23. Boom. So try. You got 6 of them. See if you can come up with cosine of theta, tangent of theta, sine of phi, or phi. I can't remember which one it is. Cosine of phi, tangent of phi. See if you can find them all. Pause the video. See if you can get them. I'm going to go through the answers. I'm assuming you've tried and now you're coming back to see if you got them right. So for theta, the adjacent is 18 and the hypotenuse is still 23. Tangent is going to be opposite, which is 11, over adjacent, which is 18. Now when we come over here to this group, we're considering ourselves at this angle. Everything's in reference to that angle. So its opposite is 18 and hypotenuse is still 23. Its adjacent is going to be 11 over 23, and the tangent is going to be 18 over 11. Notice that the sine of this angle is equal to the cosine of this one. And that'll happen in all right triangles. That's because one of the ways to look at it is to keep in mind is these two are what we call complements of each other. They add up to 90. So you can try it on your calculator. By the way, calculator finds you all these values. If you want to try some particular angle, if you want to do the sine of, let's say, 42 degrees, and compare it to, on your calculator, the cosine of, let's see, what adds up to, it's going to be 48. Its complement is 48. So if you find the sine of that angle and the cosine of this one, you're going to find that they're the same. Because those two angles add up to 90, just like these two have to. And one's opposite is the other one's adjacent, and you get this effect. So try the problems and move on to the next thing.